All right, thanks everyone for being here for the demonstration and lecture on quantum. I'm Dr. Duncan Earl. I'm the President and Chief Technology Officer at Cubitech. So today we're going to talk about quantum technology, and we're going to see some demonstrations. It's just kind of a taste of quantum to help everybody kind of understand a little bit more about the technology that underpins this revolution in information science. I'm going to tell you right off the bat, I'm really nervous about this class. And the reason is we had a talk about this months ago, that we really need to get quantum into the high school regime. Normally this is taught at kind of the senior level in college, or even sometimes in graduate school. And I thought, I agreed 100%. We've got to get this down to the high school level so we can get exposure early on. And then they said, well, why don't you teach a class on it? And I thought, that's a terrible idea, but I'll give it a shot. I'm not a high school teacher. I'm not a professional teacher. Those guys are incredible science teachers in the high schools, do a great job. And so I hope you will bear with me. This is sort of new territory for me. But I'm looking forward to at least trying, and we'll see kind of how it goes, and we'll learn from the process for sure. As I go through this presentation, we're going to have some demonstrations. You guys can just ask questions if something isn't making sense, especially if something isn't making sense. Please just raise your hand and say, what's going on there? You know, I've got a question about this. Something isn't quite right there. Okay, so let's charge in with just a little bit of an overview of kind of this revolution that's coming. I'm an old guy, 51. You know, these phones revolutionized the lives of most of the people in my generation. When there actually was a time before the internet. When it came out, it really sort of changed everything about our lives. In the past, if you were going to go play video games with your friends, that meant you went to the arcade. You know, you had to physically go somewhere. There wasn't streaming services or things like that. Went to movie theaters. So that was our revolution, and now a new one is starting. It's really kind of a repeat of the computing revolution, but it's around quantum. And so we've got quantum computers that are coming out, quantum communications, really kind of quantum networks that are emerging, and these quantum sensors, which we won't talk as much about today. It does feel a little bit like I'm just putting quantum in front of everything, but that's really what is happening here. Technology that we used up to this point was sophisticated. It used classical bits, but now we're diving down to where we can use even more interesting physics at the quantum level. And we'll talk about that physics and look at how we can experience it some today. So just real quick description of who I am. Again, I am not a high school science teacher, so please bear with me. But I am the President and Chief Technology Officer of a company I co-founded, which is really in this quantum space. I've been really privileged to be able to basically be a witness at Senate hearings and to give testimony at different events. I am a graduate of the University of Tennessee, so I currently live in California part of the time, where my company is headquartered, but we recently opened an office here in Tennessee, and I'm a former graduate from UT. Received all my degrees from the University of Tennessee in Knoxville, and I graduated from Rutledge High School, which is about 100 miles north of here in a county called Granger County. It's where Granger County tomatoes come from, world famous Granger County tomatoes. But it was a rural school that ultimately I started out, had a great science teacher that got me excited about, at the time, believe it or not, quantum or particle physics was just sort of being taught in his class, and that got me really excited, and from there I went on and became a physicist and do what I do today. So I'm here to join you to see if I can maybe pass that along. The excitement I had when I was a senior in school really propelled me into what I did, and I hope we can do a little bit of that today. The other reason I'm here is because we got a real problem on our hands in the United States. Everybody is trying to go after quantum. The Chinese, the Europeans, there's a fairly competitive landscape. Yes, question?
What is quantum stand for?
So quantum is really just the science of the very small. A quanta means kind of the smallest amount of energy that you can measure, and it's indivisible. And so they came up with quanta originally, and they extended that to quantum physics. And that's kind of where we're starting from. Yeah, that's a good question. As I was saying about the countries that are in the U.S. right now, or countries in the world today that are pursuing quantum, there's a huge race that's on. And the reason why there is a race is whoever can harness this technology first, whoever can really build the products and the early systems around quantum, those countries are going to own really all the technology that comes out in the next 100 years. So we would like the U.S. to be that country. We at least would like the U.S. to have a major lane in dominating and working in this space. Obviously, anybody think of any of the countries that are our competitors that might be putting an effort into this? Any guesses?
Russia?
Russia has an effort. Yeah, they're great software programmers. If they can come up with greater, computational power, they can do even more with it. Any other guesses? China. China outspends us significantly in this area. They put out more PhDs, they put out more papers, they put out more patents. They've built a larger quantum network than we have. They've done quantum in space so they can go between continents. These guys are really working hard, guys and gals, are working really hard to become at the forefront, be at the forefront of the quantum space. So we've got to keep up, and we're a little bit behind. And so that means that we've got to train our people very quickly so that they can be part of this quantum future. And because quantum is such a weird, it's strange. You're going to see it as we go through here. Einstein called it spooky action at a distance. It's a very strange physics. And so the earlier you can get exposed to that, the better able you will be to kind of work with it. Yep, another question? Quantum, say that again? Oh. So yeah, the quantum space is really the whole kind of industry, the science, the academics around it. It's really the whole community of quantum. And quantum community might have been a better word to use there. But yeah, that's really the idea, is that we know this space or this community is growing quickly, but we've got to support it with skilled workers like yourselves, hopefully yourselves, over time as we introduce more and more people to it. When I started in this field, there's like a few hundred people that did quantum. It was really kind of specialized and not particularly popular. But over the last decade specifically, we've seen billions of dollars put into this space, and the focus there is on really growing a market for quantum. And that is where we need people like yourselves. We need everyone that is interested to help and support. Okay, so with that, that's kind of the pitch for why you should care about quantum. We'll talk a little bit later on about what you can potentially do and what it pays and things like that when we take some questions a little bit later. But that's at least the introduction for quantum. Has anyone heard of quantum computers before today? That's not bad. I just did a thing earlier this morning, and it was a pretty limited number of people that had heard about this. You're starting to see it more in in the newspaper, and well, nobody reads the newspaper anymore. Online, on Google, definitely on the news. So we're starting to see more about quantum computing. Anyone heard of quantum networks? a little less popular. So quantum networks are just as important. They kind of link together the quantum computers. They also enable other technologies. But quantum networks is a growing area. And it's where the Chattanooga kind of fits into the picture. So as we go through this presentation today, I'll try and give you some context about what's happening in quantum and how our area fits into it. Okay, in order to do this, I'm going to have to give kind of an overview, a little quick history on light. We're going to do some experiments to learn about photons, and then we'll talk about the bizarre physics of quantum. So light has a really long history. Like 2,000 years ago, people were trying to figure out what light was. They used to think that maybe it came from people, like light came out of my body or something, and that's how come your eye was able to see me. Now, that's pretty easy. You put somebody in the dark, and that's not working anymore, so no more light's coming out of them. But they had crazy theories. They thought, well, maybe when you're in a dark place, it can't get out. They had all kinds of strange ideas, but eventually they realized that light really comes from the sun or from other sources, and it's something that looks like a wave. Maybe it's a particle, but it's some sort of material, some sort of media that hits us and bounces off and allows us to see things. So early on, the question became, what exactly is it? Is it a particle or is it a wave? And there's a long debate on that, which I won't go into for brevity for this course. But for the discussion today, I'm going to treat it as a particle, which means this light bulb above me is putting out billions and billions of photons. You can think of them as like little BBs, little particles of light that are bouncing around. When you go outside and the sun hits you in the face, it's like those little tiny BBs hitting you all at one time. But what they found out early on with that type of model is that those little BBs, those little particles, which they called photons, those photons are indivisible, which means you can't cut them in half. You can detect a whole photon, but you can't detect half of a photon. They're always coming as a group. If you have a brighter light source, it just has more of those photons. But they're all individual, small little BBs, if you will, that you can't cut in half. Does that make sense? Okay. Well, we're gonna test that a little bit, and we're gonna measure them. But if I turn my phone on and use my flashlight, you guys all see the photons coming out. They're all different colors inside this white light source. But I can transmit these photons through the air, or I can actually transmit them through a material, right? I guess you guys have probably seen, optical fibers before, and light goes in one end of this optical pipe, and it comes out the other side. So these are really big fibers, so we can see them a little bit more easily, but they make them in very small fibers as well. And so on the table here, I have some smaller fibers. Everybody see that there in the back? So these ones, everything that we're going to do today is actually going to use these optical fibers. And just like these big ones, they're doing the same thing. You put light in here, light comes out the other end. Billions of photons go in, billions of photons come out. A little bit of loss, but not a whole lot. So we're going to use optical fibers to control the photons as we do some of our testing today. And you probably may already know that fiber optics we're using already. That's how we get our internet in Chattanooga, right? It comes through an optical fiber where we put lots of photons in different ways to represent information. And that's called classical bits that we send through regular fibers. We're going to define something a little different today. Okay, so millions and millions or billions and billions of photons are interesting. We're already pretty familiar with that when you go out in the sun, you're getting billions of photons hitting you. When you hook up to EPB's cable, optical cable, you're getting lots of photons through that as well. But we're going to want to taper those down. We're going to want to taper down to maybe 1 million photons or 100 photons and eventually 1 photon. Because as we start doing that, as we start looking at an individual photon, we're going to start to see some physics that is different. It's going to start behaving in ways that we don't experience as in our world. And that's where a lot of these technologies and these new advances are coming from. So to produce those photons, or single photons, I'm going to use this device here. This is a special source. It's just like a flashlight, except it costs a lot more. And it produces very, very few numbers of photons. I can't open it up, but inside of here is a special crystal that's actually made in Israel through a very complex manufacturing process. We have a laser inside of here. It runs all the light through that crystal, and then it turns that light coming in, oh, thank you, turns that light that's being pumped into the system, it turns it into these single photons or sometimes pairs of photons. And we're going to use those today, we're going to use this source today to allow us to create these photons and measure them. To measure the photon, I need something special. We could turn all the lights out here and sit in the dark for like 45 minutes, and believe it or not, your eye would probably be able to see this extremely dim source. Your eye is that efficient. But we're going to use something a little more repeatable and faster, and it's this detector here. This is called a single photon counting detector, and it can see a single photon. If one photon comes in here through an optical fiber, comes in here, there's a detector inside of here that will spit out a pulse, a little electrical pulse, through this wire. And so a single photon counting detector is a really helpful tool. It lets us tell when we have 1 photon or 10 photons or 20 photons through these electrical pulses that come out the backside. These electrical pulses are then going to go to this guy right here. Maybe just hold them up so we can see it. This is a coincidence counter, and this counter will take the pulses coming from the detector. It's just going to count them up. So it's really just kind of keeps track of how many pulses we get. So let me just kind of go through that one more time. This guy produces the photons, not a lot, just a few. He kicks them out. He kicks them out, by the way, whenever he wants. They're not coming at any particular time. They're just randomly coming out of here. We're going to run it through some fiber to this guy that detects them and turns them into electrical pulses. And then we're going to run that into this counter that's going to count them up. And we're going to be able to see that on the screen. So this is like the sort of the basic tools that you need to start exploring some of this quantum technology. So let's see if it works first, which is always a good question. I'm going to take one of these detectors here. I'm going to hook the source up to it. Are there any questions while I'm setting this up? Any thoughts? There's no dumb questions. Might be some dumb answers I might have, but if there's something you want to ask, just please ask it. Oh, one in the back.
When it comes to computers, can quantum computers take pictures?
So one of the things quantum computers is really good at, they're not necessarily good at taking the pictures, but they're really good at processing them. So say you had a picture and you had a dog in it or something, and you're trying to pick out every picture with a dog in it. It's kind of like that CAPTCHA thing where you pick out every picture that's got a sidewalk in it. The quantum computers are really good at image processing. Our techniques today aren't bad, but they're very limited, and a quantum computer could actually enhance that. Can't take pictures, but they can definitely process them and learn from them as well. All right, let's see. I've got the power to this source that I'm plugging in right now. I'm going through a fiber, and I am going to this one detector here. If I really quickly run a program so you guys can see what I'm seeing, we'll be able to look at this. Okay, so this counter has 2 channels on it, and so it can actually monitor 2 of these detectors, but I've only hooked one up for the experiment we're doing right now. And if I hit this count button, it'll take about half a second, and it'll count up as many photons as this one detector is seeing. So we're seeing about 1.5 million photons coming from this system. Again, that's 1.5 million little BBs that have made it to this detector, have been converted into an electrical pulse, and have been recorded by this counter. If I loosen up a little bit on these detectors, loosen up on these fibers a little bit, make it a little bit to where they're lossier, and I run that again, my 1.5 million is now only 500,000, right? I've lost some of those photons that I'm trying to put into this pipe and get to these detectors. So the reason I'm kind of set this simple demonstration up is I want everybody to understand that the photons, these BBs, they really are real, they do exist, and we can count them. And again, although we can count them, we can't cut them in half. They only come as a quanta of light, a fixed amount of energy. And that's where, again, that word quantum is coming from. But just detecting single photons isn't necessarily the most fun thing to do, or the most interesting. We have to kind of push that a little bit through some other optics. And so we need to talk a little bit about beam splitters. So there are lots of optical tools and optical components that are used in quantum computers and quantum networks. But at the end of the day, when you really kind of break them down, they're very simple devices. And one of them is the individual devices are fairly simple. One of them is a beam splitter. And a beam splitter is kind of like a half-silvered mirror. It's a mirror that if photons encounter it, some of them are going to transmit and some of them are going to reflect. In fact, if it's a 50-50 beam splitter, exactly half of these photons will transmit and half of them will reflect. So if I had 100 photons coming into this beam splitter in a second, how many would transmit? Any guesses there? All right, and how many would reflect? 50? All right, so that's the basic idea behind these beam splitters. And I've got one right here that I've already kind of hooked up. I've looked at one arm already. And I'd like to just run my light through that again. So we're going to have this set up on the table where my source is producing the photons. They're encountering this beam splitter, a 50-50 beam splitter. Half of them are going here and half of them are going there. And now we're going to monitor what we're seeing at each channel on the counter. So I'll hook that up next. None of this is too hard, right? This all makes pretty good sense. So it gets worse in about a minute. so let's hook this second channel up. All right. I'm going to tighten this up a little bit more so we can get our light through there. Okay. I'm setting you guys up a little bit. I'm going to just tell you that. Okay, so we're going to do this experiment one more time. This time I'm going to get the program running here. Okay, hit the count button. And again, I've got 2 detectors this time. Oh, did I lose one? 2 detectors this time that are going to be monitoring counts. There we go. Okay, that's a little better. Let me hit that again. Uh-oh. Okay, I might have to have somebody come up and read this. But basically, we have 2 channels that are being produced here. And one of them is seeing 1.3 million counts. That's channel 2. And the other one is seeing 800,000 counts. I'm not sure why it's not showing up on channel 1. I wrote the code myself, and I am a physicist. So I'm not a software programmer. So maybe that could be the issue. But could I get somebody to come up and at least confirm it? Somebody, I don't want to wave my hands. You look like you're up for taking a look. Appreciate you being my eyes here. Yeah, you can actually see it from the front, I think. So on channel 1, what are you seeing there? Is that one right there?
1.366.0.
Okay, and on channel 2, what do you see?
841.394.
If I click this button and do it again, basically kind of the same numbers, right?
Basically the same.
That's perfect. Thank you. Thank you for making up for my bad programming. So, so we're seeing a split. It's not quite 50-50, right? I mean, it would be nice if it was 1 million here and 1 million there. It looks like we're getting a little more in one channel and less in the other. But the reason why we're seeing that split is the beam splitter is taking all of those BBs that are coming in, sending one to one side and one to the other side. Now, when they make these detectors, some are more efficient than others and some are less efficient, and that's why we see a difference. Oh, thank you. So that's why we see a difference. And is this on, Jed, as well? Okay. So we do have this ability to kind of split these photons into these separate paths. They're all single photons, they're all indivisible, and they're all encountering the same beam splitter. Now, this is where it gets interesting. So let me just ask a couple of questions and make sure we're all on the same page. So in this experiment, in this demo that we just did, we know that there's millions of these BBs that are being split between these 2 detectors, and we're seeing the outputs there. Again, can one of those BBs be cut in half? No. All right, that's great. So now I want to ask a more interesting question, which is, let's say I reduce the intensity of this source so that instead of sending millions of BBs, I'm only sending 1, just one BB coming out of that blue box, that's going to encounter this beam splitter, which means we can either transmit or we can reflect. What is going to happen to that one BB? That one BB that you can't cut in half. Is it going to transmit or is it going to reflect? Any guesses? Transmit? Maybe anybody think reflect? Yes. So here's the bad news. We don't know. We don't actually know what's going to happen. There's a 50% chance it transmits and a 50% chance it reflects. And when physicists found this out, they were very upset because physicists like to be smart. They like to know everything. They like to have all the equations, and if they have a big enough computer, they can calculate everything. But this is a super simple problem where physicists couldn't give the answer. Half of them said it's going to transmit, half said it would reflect, but they couldn't prove what was going to happen. And what we find out when we do this experiment, and we could do it, I could dim that down and we could do it all day long, is that 50% of the time it reflects, 50% of the time it transmits. It's completely random. We don't know what's going to occur, and that's kind of this inherent randomness that occurs in nature. Well, that causes other problems in physics. It's not okay for sort of there to be something in the universe that we're not able to predict. We need to have some way to formulate it, to use mathematics to describe it so we know what's going to occur in the future. And so what quantum physics found, and what has been proven through many, many decades of experiments in physics, is that something very strange happens for this particle. Now keep in mind, this isn't for us. This is for particles, these little BBs that are really, really small, that exist in a strange kind of physical world. But what we found is that when the photon comes in, it reflects in one universe, and in another universe, it transmits. And those are two kind of separate realities that coexist at the same time. And so I'm going to call this the multiverse. They actually call this the many worlds theory in quantum physics. But you could actually do this many, many times with this photon with more complicated setups to where you could take one photon and push him into 1,000 different worlds. You could push him into the multiverse. Now, you guys are probably like, yeah, okay, no problem. It's the multiverse. I saw that on Marvel, and it's no big deal. But for everybody that's a little older, it's like, that doesn't sound right. That seems very strange. But that is essentially what is happening at the quantum level. And that's really, really powerful. If you can push a photon into these other universes, then they're all going to be experiencing different things that you can eventually bring them back, interfere them together, and learn things from. So if you're building a computer, and you want that computer to be really fast, don't just have one photon doing one operation, then doing another, and then doing another. Push it into 1,000 different universes where it does different operations. Bring them back together again, and now you've solved the problem a whole lot faster, if that makes sense. Any questions on this sort of problem, this kind of question, this issue? No thought? Everybody's cool with the multiverse? All right. I figured you guys would be concerned about it. Question in the back there. Yeah, that's a great question. So they call this superposition, and we've put the particle or the photon into superposition. And that's because it's the easiest to do right here on this tabletop. But you don't have to just use light. You could have done, we could have taken an electron or a proton, any other small particle, maybe even a whole atom. People have taken a whole atom and done this, maybe even a few atoms. At some point, though, you get bigger and bigger and bigger, and you can't do it anymore. And where that breaks down, we're not really sure why or where that occurs. So we keep building bigger and bigger ensembles of these things, putting them in superposition to show that. But I think we all know I can't be in multiple universes at the same time. You guys can't be in multiple universes at the same time. All that Marvel stuff, that ain't going to work. But we can definitely do it with these small particles. And so that's why these particles are so important. That's why we're trying to harness them. We can't do it at the big level, at the macro level, but we can at this very small quantum realm. Yep.
So would it ever be possible to go bigger?
So they are already going bigger, and nobody knows kind of how far you can go. But we can do this with atoms, which are definitely bigger than a photon. A photon's really, really small. But going to 1,000 atoms, 10,000 atoms, we're not sure how much further we can push it. Yep. Oh, thank you. Yeah, the question was, could we go bigger than just, an atom or just a photon? And we can, we just don't know exactly how far. Sorry, next question. Sorry, say one more time.
Are there other things like photons that do the
So yeah, it has to be a quantum particle. So electrons are so the question was, could there be other particles we could do this with? And yeah, a particle like an electron or a particle like a neutron, those are all still very tiny. As long as it stays tiny, we can do it. Yeah, those are good questions. So this property here is called superposition, and it's one of the fundamental kind of properties that we're utilizing for quantum computers. And I hope everybody kind of understands that being able to push things into that multiverse allows us to speed up computers, because now it's like you have 1,000 computers all working on the same problem. And you didn't have to build 1,000 computers, you only have one. So it's a really big advantage computationally. There's also something else called entanglement, and we actually have some really cool demonstrations of this, and if you go to some of the colleges that use our kits, you actually can see this in practice. We won't be able to do it here today for time, but entanglement is kind of the inverse of superposition. So superposition is when you take one photon and you send it into lots of different paths. Let's just say 2 for now. 2 different paths, 2 different universes. Entanglement is kind of the opposite of that. It says you take 2 particles that exist in our reality, you separate them really, really far away so they're not even anywhere near each other. There's no way they can talk to each other quickly because they're so far away. And then when you mess with one, the other one does similar things, or it feels the same effect. That's called being entangled. They're entangled particles. And those are what Einstein called spooky action at a distance. It's this idea that you could have 2 particles that look like they're 2 distinct people, or two distinct particles, and when you do something to one, the other one, no matter how far away it is, instantaneously feels that. And so entanglement is the complement to superposition. That's how we make really secure quantum communication systems. And if you think about it, if I have a photon and you've got its twin, and I do something to the other one and you see that impact, it's almost like we have a quantum walkie-talkie or something, right? But there's nothing communicating between us. So there's no way somebody can come in and intercept it or crack that code. We've got like this secret bond that nobody can infiltrate. So security comes out of entanglement as well as being able to tie together quantum systems. And for that reason, these particles that have these kinds of properties, we call them quantum bits. So the basic bit of information for quantum systems, so we call them quantum bits or qubits. And that's what we're trying to harness with all of this new technology. So as I said at the beginning, we have 2 really powerful new technologies that are being built from qubit systems. You guys in your lifetime are going to see them, you're already starting to see them have an impact on what we can do. But the first of them is quantum computers, where they exploit this multiverse to perform calculations faster. And then the second are quantum networks, where we use qubits to have better security, entangled qubits to have better security, and to allow us to interconnect quantum devices. And these systems are just being built. One advantage is that you guys and gals, you folks have here in Chattanooga, is that the very first commercial quantum network has been built in Chattanooga. And this is for the entire United States. There's only one of these in the United States. So I'm sure you've heard of Bill Gates and Steve Jobs, right? Those guys were smart guys, for sure, but one of the biggest advantages they had is that they had the first computers, early mainframe computers, right in their backyard. Bill Gates was programming a computer at 16 when nobody else had access, really, to some of these very large computers in the early days. So it's true for us here in Chattanooga that we have access now to a resource that nobody else does. They don't have it in San Jose, San Francisco. They don't have this capability like we do here in Chattanooga, which gives us a significant advantage. If we can get more people in the Chattanooga area to learn about quantum, to choose it as a career path, to become part of this new industry in quantum, and then to leverage what we have in our own backyard, we can create more Steve Jobs and Bill Gates right out of this area. So we want to try and harness that potential, that possibility. And that, of course, is why I'm here. This is what one of them looks like. If you want to go visit a quantum network, it's not too far from here. You can actually whenever there's an open house tour at EPB, this is kind of what one looks like. It's behind glass, it's behind retinal scanners, so you can get in there and work on the equipment. It's very fragile equipment, so it has to be very carefully protected. But these racks contain all of the quantum equipment that's needed to generate qubits, to route them around a network, and to connect them with different devices. The same technology that you're seeing on this table, just think of it on, that technology on steroids is basically behind here. And so we need people that can help us install these, maintain them, make better versions, actually manufacture the components that we're using today. Yeah, and if you ask yourself, okay, I don't really like physics. Is this, something for me, or do I have to be a physicist to do this? The good news is you don't need to be a physicist. In fact, to be honest with you, I think we kind of have enough physicists working on this already, and there's more in the pipeline. But there's a whole bunch of other things that we don't have. If you want to get a PhD in physics, they'll still have a job for you. But we need engineers of all types to support this. So if you have an interest in becoming an electrical engineer or mechanical engineer or materials engineer, you name it, it's got an application to quantum, and there's a big need for those engineers today. Also, people that manage networks and are into IT specialties, those types of jobs also are needed to support this industry. If you like developing software, well, the new software that will be developed in the future will be on a quantum computer, and we need software developers that are focused on that. You might have seen earlier the fibers that were part of the EPB quantum network. EPB puts fibers all across the county, and now they're learning how to do that for these quantum networks. So fiber installation technicians that also have a specialty or an understanding of quantum are going to be needed to support that growth of that network. And then these little blue boxes and these little black boxes, all of these components that are in those racks, they're made by companies that need workers that really understand what quantum is, at least at a certain level, so they can support the manufacture of those components. And then finally, we need maintenance around these networks and support for all the networks that are deployed. One day, there will be a quantum internet that provides these incredible capabilities all across the country, but it's going to start here in Chattanooga. And so if we can develop the workforce to support its growth, it's going to really help the region and the country. So just some final thoughts, and then we'll go ahead and take some questions. We're just at the start of this revolution. Just as my generation got really excited about video games and the internet and these little cell phones, you guys are embarking on a whole new technology that takes it even a step further, where we're harnessing the power of this quantum realm to do things that were never thought possible before. We need your help to deploy and advance this technology, so if you have ever thought about going into a technical space or ever thought about learning more about quantum, there's lots of opportunities in the coming years to make that your career and to really support what's going on. Chattanooga as a whole is doing a great job at mobilizing all the resources in Chattanooga to help sort of pave that way for people that want to get into this space. We just had a big event in Chattanooga about 3 weeks ago where major companies like IBM and Google and Microsoft were in town to see this quantum network and to learn more about how they can work within Chattanooga. So these could be jobs, potential employers down the road that we want to make sure we've got a trained workforce for. And it's just starting, so you haven't missed the boat. Everybody's just now trying to figure out the same questions we're trying to answer today. So it's just starting, and you can be part of that process and really make a big impact. Hopefully another Steve Jobs or Bill Gates comes out of that effort, as well as lots of other engineers and support for these systems. So that is the last slide. I hate to kill you with a bunch of slides there, but that's the last slide from this presentation. If I just take your pulse here for a little bit, the single photons, how they produce qubits, how we use those qubits to push into this quantum realm, into these other multiverses, and how that speeds up our processing. Is that resonating at all? Does that sort of make kind of sense to you guys? Yeah? Oh, not too bad? All right, question in the back?
This is one question that Corey told us. Is quantum teleportation possible?
Yeah. Oh, I love this question. This is great. And the answer is yes. The short answer is yes. But the question is, to repeat the question, can we do teleportation? with this technology, and it turns out we can. So teleportation sounds like something out of Star Trek, where you're beaming somebody up. Right now, we can take these small particles that we're passing around on this table, and we can actually have them teleported to a different place in space using this technique called quantum teleportation. The way it works is we take a photon and we basically kill it. We crush it and squeeze all the information out of it, and when we're done, there's nothing left of it. And that information gets sent to another particle that basically gets written into that new state or that new particle. So you have one particle where you take all of its information, you kind of remove it from the particle, which kills the particle, and then it gets recreated at another particle somewhere else. And that other particle looks identical to the first one. And so you can do that with a single photon. They're starting to be able to do it with bigger things. Eventually, we'd love to be able to do it with people, but I don't know if that's going to really happen. But so quantum teleportation is possible, but it's really just for tiny, small things right now. Any other questions? Yeah.
Okay, using quantum computers, will we be able to communicate with a different universe?
So yeah, so that's one of the sort of immediate questions people have when they think about quantum communications. If you really can have this bond between two particles, is could you push one out there, out somewhere into the universe and still have some communication with it back here on Earth? One of the challenges with that is you can, but it's just kind of all noise until you're actually able to communicate classically with it. So that means we still have the same limits with quantum communications in terms of like how far we can reach with our communications or how quickly we can send communications. So I don't think it will let us reach out to those other spaces or to distances that are very, very far away any more than what we have today. But this is a new field that's changing quickly, and you never know where it might lead. Yep. And the question was, can we use quantum communications to kind of reach out to other universes or to distances really far away? Any other questions I can answer? There's no dumb questions. So one there in the back.
Do you think in the near future they'll be able to bring the teachings of quantum to high school? And I want to know what you guys could do to try to make that process a lot faster.
Yeah. So the question is, and I'm repeating this for the guys online, can we pull quantum into high school education faster and make it very clear and easier to adopt? I think the answer is yes. Today, we did some experiments on this tabletop, but the real experiment is this. Could we have a conversation where we're introducing some of these concepts in the 11th grade, 12th grade, maybe even earlier? And I think the answer is yes, but it's going to require all of the academic organizations, the teachers at the college level, at high school level, even the elementary level, to pull together and figure out how to do that in a coherent way. I, again, am not an educator, so it seems like a really hard process for me, but I know we've got fantastic teachers that are dealing with those questions all the time. I'm sure we'll be able to introduce people to it earlier. And then, 10 years from now, somebody that's 16 or 17, they'll be like, oh yeah, quantum, yeah, you got the superposition principle and entangled light, and yeah, of course, I was using my quantum computer last week. So, you'll have that kind of thing occurring. So it'll be very sort of mundane, hopefully, in the near future. Any more questions I can answer? Yeah? Hey, that's a good question. How much money can you make? That's a really good one. So right now, Glassdoor is like a survey company. They survey people today that have different jobs, and they ask them, if you're doing quantum, what are you making? And the average quantum practitioner is making about $125,000 a year. But that actually seems kind of a little low for what we've seen. There's a huge demand. Companies today in the quantum space, they have lots of problems, but their third-ranked problem, the thing that keeps them up at night, the third item on their list, is getting enough employees, getting enough staff, enough engineers, enough technicians to build what they need to build. So that means all the quantum companies today are fighting over anyone that can help in the quantum space, and that's going to drive that price up. Sorry, question?
So basically, quantum companies are willing to give the money, they just need the people?
So the question is, are the quantum companies basically ready to employ people? They just need the people? And the short answer is yes, that's right. There's a huge deficit of people that actually know much about quantum and can be involved in that process. And again, that doesn't mean you've got to be a PhD physicist to do it. Even people they're just building sort of the basic components and on our manufacturing line, they need them to have experience and skills that are in the quantum space. If they can find them, they'll pay for them. Yep, another question? Okay, so the question was, how long could it take to get to that position? The glass door quote that I gave you, that 125,000, was kind of an average. So that probably includes people that are more on the technician side. Maybe they've gone through some community college, maybe they've gone through a certification process. They're probably a little bit lower on that end of 125,000, but it also includes the engineers that are in there that are probably in excess of 125,000. And the engineers are spending 4 years, maybe 6 years after they graduate from high school to get that training and that education. So it really varies a little bit. The more you stay in school, the higher you are on that salary range. Yep. Another question in the back?
I didn't quite understand your answer on the teleportation question.
Okay.
When something is teleported, would it be destroyed and reconstructed on the other end, or would it be completely destroyed and a copy is made?
Yeah, so the question is, on teleportation, is it completely destroyed and a copy is made, or is it just transmitting sort of information to where something is lost and then it's regained somewhere else? I'm trying to rephrase that a little bit. And the answer is, for teleportation to work, you have to completely extinguish the original particle. And once that information has been taken from the particle, you can't record it or anything. All you can do is send it somewhere else to be reconstituted, to be turned into another particle, which means you can't take that information and then say, I'm going to send one here, one here, one here, and make 3 copies. The way the quantum physics works, it will keep you from making copies. It only allows you to destroy and then make one new version with teleportation. Sorry, it's a really complicated answer to the question, but does that help any with it? Okay. Yeah, I would love to be able to make multiple copies of myself with teleportation, but it looks like the physics is fighting us on that one. Another question.
How many times can you destroy with the same information?
Yeah, that's a good question. So the question is, how many times could you destroy a particle and make a new particle, or the exact same copy of that particle? And I think you could do it as many times as you wanted to. I mean, the process for breaking down a particle, getting the information, and then recreating a new one can be repeated over and over and over again. Yeah. Another question in the back?
I did hear when you mentioned about transporting photon to a whole different place,
Right.
and that could be as fast as the speed of the light, probably.
Yeah.
So when you say using quantum computers or quantum internet, would that also change the speed of connections and how I can send a message from here all the way to a different country or a different continent? Would that speed also change?
So the question is, does the speed of communication change when you can do teleportation? And that is a perfect question to ask, because I will tell you, when I started my company 10 years ago, the first people to show up were some guys from banks. And they said, listen, we got this communication link with the stock market. If we can make it faster, we can make billions and billions of dollars. It's called high-frequency trading. And they said, we want to just teleport the information. We don't want to run through these fibers and run only at the speed of light. We want to actually teleport it so we can beat everybody to the punch. And the physics of quantum mechanics really prevents that. You can teleport things, but they just look like noise until you can actually classically, over the speed of light, at the speed of light, communicate information. So if you just wanted to transmit noise that nobody knew anything about, you could do it. But if you want to actually transmit information, it still is just at the speed of light. Yeah. But yeah, and that's a good question. Like, can you break the speed of light? Nope. No one's found a way to break the speed of light, so including for information. Yeah. All right. Any other questions? All right. You guys have been a great class. I really appreciate you bearing with me and learning a little bit more about quantum. We'll have a chance, I think, after this is over, for others to come up and sort of press the buttons, see the devices, ask some more questions if you want to. But thank you so much for taking the time and listening to us talk about quantum. All right.